right, linear optimization. This is the last section in our chapter. I've also seen it called linear programming. But what linear optimization does is it finds the maximum or minimum of some function given some constraints in the form of inequalities. And the general steps are this. You're going to graph and shade your inequalities first. And you should have a shaded region where all of the inequalities overlap. You find the corners of that region, and then you plug those corners into the function that you want to maximize or minimize, depending on whether you want the max or the min or the high or the low or something like that. So here's a problem that says find the maximum value of this function. So this function right here, this equation, I maybe shouldn't call it a function. I guess it is a function. This equation is where you plug the corners. Plug your corner coordinates here. And in order to find those corners, I need to graph these four inequalities. Now, I do see that x and y are both greater than 0, which limits me to the first quadrant. So when I graph these, let me see, I'm going to give myself some room to put a lot of stuff in the first quadrant. So let's see, let's put that right there. And let's graph these lines. My first one is negative x plus 8. That's a y-intercept of 8, so I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8. And a slope of negative 1 means down 1 over 1. And these graphs need to be as accurate as possible. So, and for that reason, I carry a lot of points down. Normally, when I'm graphing lines, I'll just do maybe 3 points. When I'm doing these inequalities, these linear optimization problems, I'm going to use as many points as possible because my graph needs to be almost perfect. It is a solid line because we're also equal to. And this one we're going to shade down. Y is less than. You could also plug in the ordered pair 0, 0. And if I do that, I get 0 less than equal to 0 plus 8. And that is a true statement. So I will shade this way. So I'm going to shade this way for the red graph. And then I have 2x minus 4. That's a y-intercept of negative 4. So 1, 2, 3, 4. And a slope of 2. So up 2 over 1, up 2 over 1, up 2 over 1. And I continue that trend. And then I'll connect those points. There we go. If I plug the origin into that equation, I get 0 is greater than or equal to 0 minus 4. Again, that's a true statement, so I'm going to shade towards the origin. And you don't want to go too crazy with your shading because you need to be staying in touch with or in tune with where the shading overlaps. So right now I've got this region right here where my red and green are overlapping. Then let's do x is greater than 0. Well, if you graph the line x equals 0, that's a vertical line. So I'm going to graph my vertical line at 0. And then if x is greater than 0, that's going to be things to the right. So now I'm going to shade this way. And you have to be careful because now my shading is getting all over the place and kind of crazy. So I'm always trying to be aware of where the shading overlaps. And right now that's in this triangle right here in the middle, right around in here. Then my last one is y is greater than or equal to 0. That's a horizontal line. And we will shade up. So now I'm going to shade up. And if I shade that up, my final overlapping region, so I shade this one up, my final overlapping region, and yet, man, that's such a mess. Look how messy that is. My final overlapping region is this region right here. All of that. Wow, that's kind of bad. Let's erase that there. So this is where my shading overlaps, and I need that common region right there. Then once I find my region that's contained by all of those inequalities, I write down the coordinates of the corners. I have a corner right here. I have a corner right here. I have a corner right here. And I have a corner right here. Those corners are the ordered pair 0, 0. Then I have 2, 0. Then I have the ordered pair 2, 3, 4, 4. And then I have the ordered pair 0, 8. Those are the four corners. And then one by one, I plug those corners into the original function, f of xy equals x plus 3y. And so if I plug in 0, I get 0 plus 3 times 0. If I plug in 2, I have 2 plus 3 times 0. If I plug in 4, 4, and I'm plugging in for x and y, x plus 3 times y, which is also 4. And then I have x plus 3 times y, which is 8. And I work those out. 0 plus 0 is 0. 2 plus 3 times 0 is 2. 4 plus 3 times 4, that's 12. Plus 4 is 16. And 0 plus 3 times 8 is 24. Now that I've done that, I go back and I read the problem, because it's always good to read, builds character. I need the maximum. Now here's the really tricky part. Maximum means big. So we want to circle or point out the ordered pair that gave me the largest value for the function. So my maximum, I achieve a maximum value. And I did specify the maximum value. The maximum value is actually 24. And it occurs at the point 0, 8. And so that's how these linear optimization problems work. You graph your inequalities, find the shaded region, and then you plug the corners of the shaded region into your function. So there's problem number 1. Let's try a second one. Same thing, find the maximum and minimum. Now, that doesn't mean you have to do a whole lot more. It's just now you're going to circle the largest and the smallest number once you get to the end. So let's work this one out. Um, let's see, y is less than or equal to 6. And I'm looking at these two equations also. These are not in slope-intercept form. I kind of prefer to graph out of slope-intercept form. There are other techniques, so I'm going to put these in slope-intercept form, and before I do that, I'm going to give myself a little bit of room to work. There we go. Let's see, so this one I'm going to move my 2x over, subtract 2x, and that's going to give me negative y less than equal to negative 2x plus 2, but then you need to divide everything by negative 1. Divide negative 1, divide negative 1, divide negative 1, which gives you y, and I divide it by negative, so that flips to greater than equal to positive 2x minus 2. This one's not going to be as hard to solve. I just need to move that 3x over. So I'm going to subtract 3x. Negative 3x minus 12. Are you kidding? Negative 12? How am I going to get all the way down to negative 12? Who created this problem? Oh my gosh. Okay. Well, let's see what happens here. Negative 12. Who's ever heard of such precocity? I've also got to get up to 6. This is a bad problem. All right, let's see what happens. I'm 8 minutes in. I'm not going to change my video now, or change my problem. Let's see. Got a y-axis. I need to go up to 6 and down to negative 12. I have a feeling that I will end up needing to change the scale, and this is going to be a little bit tricky. My y-axis is going to go by 2s. I'm going to go by 2, and then 4, and then 6, negative 2, negative 4. But my x-axis, I'm actually going to continue and keep those as 1s. So now I should be able to graph this. Y less than equal to 6. So y less than equals 6 is going to be a horizontal line at y equals 6. I'll do this in red. I'll do it in green, red, yeah. So y equals 6 is right here. Remember, my y's are going up by 2, so I have 2, 4, 6. And if y is less than, I'm going to shade down. Now, when I shade down this time, rather than drawing huge lines, I'm just going to draw little arrows showing that I'll go down. That keeps it a little bit cleaner. Of course, you can do it however you want to. Then I have 2x minus 2, so that's y-intercept of negative 2 right here, and a slope of 2. Okay, be very careful here on this one. This is a bad problem because now I've got to be uber careful. I need to go up 2 and over 1 for my slope of 2. But remember, one box represents a jump in 2 for my y. So if I go up 2 over 1, it's actually going to look like this. Then I go up to 2 over 1. Up to 2 over 1. And that's because I changed the scale on my y-axis. So up 2 over 1. And there's what that line is going to look like. So little poor foresight on my part when I wrote this problem. But okay, there's y greater than or equal to x minus 2, and we will shade that one up. That's going to shade this way. And all the time I'm graphing, I'm looking at where my common region is. Right now it's this little region right here. And then 3x minus 12, I need to go down to negative 12. So negative 2, 4, 6, 8, 10, 12. And then a slope of negative 3. Again, we have to be really careful because if I go down 3, that's actually 1.5 and over 1. That's a slope of negative 3. Down 1, 2, 3, over 1. And then I need to actually carry that the other way. Up 1, 2, 3, over 1. Up 1, 2, 3, over 1. Up 1, 2, 3, over 1. Now I'll connect those. And that is going to look like this. And y is greater than, which means I'm going to shade this way. And I see my overlapping region is this triangle right here. So there is the region that they all have in common. And I'm going to find the corners of that region. And you have to be careful because this looks like right here. This corner looks like the ordered pair 4, 3. But remember, up 3 actually means 6 on my y. So I have a corner of 4, 6. Then I have a corner of negative 1, negative 2, negative 2, 4, 6. So negative 2, negative 6. And then I have negative 1, 2, 3, 4, 5, 6. And then up 2, 4, 6. So that's negative 6, 6. Lots of sixes there. That's exciting. Everybody loves sixes. It's like the number between 4 and 7. All right, then we plug those corners into my function, 5x minus 6y. So 5 times 4 is 20, minus 6 times 6 is 36. That gives me negative 16. 5 times negative 2 is negative 10. Negative 6 times negative 6 is plus 36. That gives me 26. Then 5 times 6 is 30. 6 times my y-coordinate of 6 is 36. That gives me negative 6. And so I now look at those, and my maximum value is 26. So my max, I have a maximum value of 26 at the ordered pair negative 2, negative 6. And then I have a minimum value of negative 16 at the ordered pair 4, 6. So there are the answers to that one. I'll try not to be that mean to you where you have to do these crazy scales on the y-axis. And then the last problem I wanted to do is going backwards where you don't have to find a maximum or minimum, but I just want to see if we can go backwards and find the equation of these lines, keeping in mind where they're shaded. The easiest one, all right, so the easiest one for me is the vertical line, and that vertical line is occurring at x equals 2. So I see a line of x equals 2, but I'm also shading to the left of that line. So instead of x equals 2, I'm shading numbers to the left of 2. Those are numbers less than 2, and it will be also equal to because that is a solid line. Then I'll look at my other lines. I'll look at this one, and if I look at the slope going down, that's a slope down 1 over 1. So that's line y equals, I'll write it down here, y equals negative 1x, and the y-intercept is 0, or you could just call that negative x. And then I'm shading above the line y equals negative x, so that's going to be y is greater than or equal to negative x. And then the last one, I'm looking at this line. I find any 2 points that the line goes through. I see this one, and I see this one, and that's a slope of up 1 over 2. So that's a slope of y equals 2x, and a y-intercept of 2 also. And then I'm shading below that line. If you shade below, that's y is less than or equal to 2x plus 2. So that would be your answer for number 3, where you're just going backwards. You're finding the equation based on the graph. So there you go.